this video, we're going to jump ahead a little bit, and we're going to talk about organometallic compounds. The reason we're doing this now is because for the organometallic compounds that we're going to look at, their preparation and the substrates that they react on are very often alkyl halides. So it's a convenient place to stick this in. And as we'll see, organometallic compounds are going to give us some really powerful tools to include in our synthesis toolbox. So the key feature in organometallic compounds is that we have a carbon bonded to a metal atom. And what's important about this is, unlike many of the other elements that we deal with in organic chemistry, carbon is more electronegative than the metal that it's bonded to in these organometallic compounds. And so that makes carbon nucleophilic. And we're only going to look at a couple examples of organometallic compounds, but they're listed here. We're going to look at organometallic compounds involving lithium, magnesium, and then also copper. Now, the greater the electronegativity difference between carbon and the metal, the more reactive that carbon will be. So the electronegativity difference between carbon and magnesium is quite high. And so when we react with an organomagnesium compound, right, we get quite a bit of reactions, right? We actually add 2 methyl groups to this substrate. The electronegativity difference between copper and carbon is not as large, so this copper-containing organometallic compound is a little bit less reactive, right? And so we only add 1 methyl group in this case. The first types of organometallic compounds we're going to look at are organolithium and organomagnesium compounds. Now, both of these possess quite a bit of ionic character due to the significant electronegativity difference between carbon and the metal atom. And so that makes them fairly reactive, and they also undergo similar reactions. So the preparation of organolithium compounds is fairly straightforward. We react an alkyl halide with lithium metal. And this 2EQ here refers to the fact that we need 2 equivalents. So for every mole of alkyl halide, we need 2 moles of lithium, because we're going to attach a lithium to our alkane, and then it's also going to combine to form a salt with the halogen atom. And so these are just some different examples of organolithium compounds that can be prepared from different alkyl halides. This first note is one more on nomenclature, but it's important to know that organomagnesium compounds are also called Grignard reagents, and you'll see this term quite often. But their preparation is also fairly straightforward. Like the organolithium compounds, we just react alkyl halides with magnesium metal. Organolithium and organomagnesium compounds are very strong bases, and as a Bronsted base, they'll react with almost any protic substance, including water and alcohols. And very often, the goal is not to react our Grignard reagent with water, and so it's often very important to keep our reaction mixture dry when we're working with organometallic compounds. So this is just a list of some reactions involving Grignard reagents that we'll encounter throughout Orgo 1 and Orgo 2. A common feature that you'll see in these reactions is that we're adding R groups to a carbon. So we're creating carbon-carbon bonds. And that's one of the reasons we often use organometallic compounds, because it's one of the few ways to easily create carbon-carbon bonds. And so here we've added an R group to this carbonyl group. In this case, we've inserted an R group into this ring, but we've created a carbon-carbon bond. And here we've added a carboxylic acid group to the end of an R group, but again, I'm creating a carbon-carbon bond. And these are just 2 additional examples, but again, the key is I'm creating these carbon-carbon bonds. The next type of organometallic reagent that we're going to consider are lithium dialkyl cuprates, or also known as Gilman reagents. So Gilman reagents are produced by starting with an organohalide, reacting that with lithium to form an organolithium compound, and then reacting that with a copper halide to form the Gilman reagent. So we have 2 R groups attached to the copper, and then we also have the lithium present. Okay, and Gilman reagents can be alkyl, they can be aryl, attached to benzene rings, or they can be vinyl, where they're actually attached via the sp2 hybridized carbon in these alkenes. So one of the most important reactions that Gilman reagents undergo is a coupling reaction with alkyl halides. And so if I take my Gilman reagent and react it with an alkyl halide, I can actually create this coupling product, right? And what's unique about this is I'm creating a new carbon-carbon bond. And so this is a way to make longer and longer alkane chains. Now, an important limitation on these Gilman reagents is they work well with methyl primary, vinyl, and aryl halides, but tertiary and secondary alkyl halides tend to give elimination products as opposed to the coupling products. One nice feature of these Gilman reagents is that they're somewhat selective. And so they are compatible with many functional groups that are not compatible with a lot of other reagents due to their reactivity. And so the Gilman reagents are compatible with groups like ketos, esters, and amide groups. So as I discussed before, one of the most important features of these Gilman reagents is that it allows us to make longer alkane chains from two organohalides. Right, if I started with one organohalide, reacted it with lithium to form an organolithium compound, then reacted that with a copper halide, that would form the Gilman reagent with one R group. If I then react that with another alkyl halide, right, I can form a bond between the two R groups.